Your agents are running naked. Let me describe a scene that is playing out right now in thousands of companies around the world. A team deploys an AI agent. The agent has access to the company's GitHub repositories, the Slack workspace, the Jira board, and a cloud provider API key. The agent is supposed to review pull requests, summarize issues, and post updates to a Slack channel. It works beautifully in the demo. Everyone is impressed. 2 weeks later, someone notices the cloud bill has tripled. The agent has been making API calls to a service nobody authorized. It discovered the endpoint by following links in the documentation it was reading. It was trying to be helpful, gathering more context for its summaries. But it used the cloud API key to authenticate, and nobody told it not to. Nobody could tell it not to because there was no boundary between what the agent could see and what it could do. Here is the uncomfortable truth about how most AI agents run today. They run naked. No runtime, no sandbox, no credencial a uselación, no audit trail, no cost boundary, no kill switch. The agent gets a set of API keys, a system prompt, and permission to call tools. Then it runs on your machine with your credentials, with no structured way to see what it is doing, why it is doing it, or how to stop it instantly. And the problem compounds when you have multiple agents. Agent A calls Agent B. Agent B spawns Agent C. Agent C makes an API call that fails, retries, and burns through your rate limit. Who authorized that call? What credentials did it use? What data did it send? The answer, in most frameworks, is nobody knows. The conversation context was recycled. The state was ephemeral. The decision chain is unrecoverable. This is not a theoretical problem. This is the current state of agent deployment in most organizations. And it is why most agent projects never leave the proof of concept stage. The technology works. The governance does not exist. Security teams block deployment because they cannot audit agent behavior. Finance teams block deployment because they cannot predict or control costs. Operations teams block deployment because they have no way to monitor, manage, or stop agents in a structured way. AgenticNetOS changes this. Fundamentally, not by adding a few guardrails to the existing model, by providing an entirely different model, a runtime where agents operate inside a governed environment, where every action is traceable, where credentials never touch the agent, where you can stop everything with one click, and where you can measure exactly what each agent costs. This is the first production-ready multi-agent orchestration runtime. And everything, every agent, every workflow, every automation is created by prompting. No code required. You describe what you want in natural language. The system designs the agent team, creates the workflow, wires the data flows, sets up the security boundaries, and starts running. You watch it work in a visual editor. You adjust it through conversation. You control it from your phone. Let me tell you how. Everything by prompting. Here is what using AgenticNetOS actually looks like. You open a terminal. You type a command, and you start talking. You say, create a monitoring agent that watches my application logs, identifies error patterns, and creates tickets for recurring issues. The system responds. It thinks through the problem. It creates the data containers your agent needs, places for incoming logs, places for identified patterns, places for generated tickets. It creates the processing steps, transitions that parse logs, classify errors, match against known patterns, and generate ticket descriptions. It wires everything together. It sets up the routing logic. New errors go to investigation. Known errors go to instant resolution. You did not write a single line of code. You did not configure a YAML file. You did not set up a pipeline. You described what you wanted in plain language. The system built it. And here is what makes this different from just asking ChatGPT to write you a script. The system did not generate code for you to run. It created a living, running, governed workflow inside a runtime. The agents it created are not loose scripts on your machine. They are processes inside a managed environment with explicit permissions, traceable actions, and controllable life cycles. 3 channels give you the same power. The CLI in your terminal, type AgenticNetOS chat, and start a conversation with the system. A Telegram bot on your phone, text it from anywhere in the world and control your agents. And a visual editor in your browser, where you can see the entire topology of your agents, watch data flow through the system in real time, inspect what every agent is working on, and understand the state of your entire operation at a glance. But the visual editor is not where you work. It is where you observe. The GUI is a window into the runtime, not the control surface. The control surface is your voice, your prompts, your natural language instructions. You tell the system what to do. The GUI shows you what is happening. This is a critical design decision. Most workflow tools make you draw boxes and connect lines. AgenticNetOS lets you speak. The boxes and lines appear automatically. You see them. You understand the structure. But you did not have to manually construct it. Let me give you a concrete example from a real deployment. A user opens Telegram on their phone during their commute. They type, "Analyze the raw HTML in the scraping place." The system agent queries the data containers, sees the HTML content, realizes it is too large to display, extracts the key content in text mode, and summarizes the findings. The user replies, "Clean up the 3 duplicate entries." The agent identifies the duplicates, deletes them. 30 seconds. No terminal, no browser, no code. Just a conversation that modifies a live production system through governed, auditable actions. Another example. A developer working in the CLI says, "Deploy the code review transition and start it." The system deploys the transition, assigns it to an available executor, and activates it. The transition begins polling for code review requests. The developer drops a task into the input container, review the error handling across the gateway and CLI modules. The orchestrator agent reads this, reasons about which modules are affected, creates properly formatted work tokens in each module's input container, and the specialist agents pick them up. The developer watches in the visual editor as data flows from the task through review, fix, test, and verification stages, all initiated by a single sentence. This is what I mean when I say everything by prompting, not just creating agents, managing them, monitoring them, adjusting them, stopping them, diagnosing them, all through natural language, all through governed channels, all fully traceable. The system has over 40 tools available to the prompting agent, creating data containers, processing steps, connections, logic definitions, querying data, deploying transitions, firing them, inspecting results. Every single operation that the API supports is available through conversation. The runtime that changes everything. Here is the core insight that separates AgenticNetOS from every other agent framework. Most frameworks give you a way to build agents. AgenticNetOS gives you a runtime where agents live. Think about the difference between writing a script and running a program inside an operating system. A script runs directly on your machine. It can access any file, call any API, use any credential it finds. If it goes wrong, you kill the process and hope for the best. There is no isolation. There is no structured way to see what it did. An operating system is different. Programs run inside it. The operating system manages memory, controls file access, enforces permissions, tracks resource usage, and provides a structured way to start, stop, and monitor every process. The program does not run on the machine. It runs inside the operating system, which runs on the machine. AgenticNetOS is that operating system, but for AI agents. When you create an agent in AgenticNetOS, the agent does not run on your machine with full access. It runs inside the runtime. The runtime controls what the agent can see, which data containers it can read from. It controls what the agent can do, which tools are available at its permission level. It controls where the agent's output goes, which containers receive its results. And it records everything, every action, every data movement, every tool call, every decision. The agent operates inside. When it needs to interact with the outside world, call an API, execute a shell command, access a database. It does not do it directly. It creates a request. That request flows through the runtime to a dedicated execution channel. The execution channel handles authentication, timeout, retry, error routing, and result capture. The result flows back to the agent through the runtime. The agent never touches credentials. The agent never makes untracked external calls. The agent never runs unsupervised. Everything goes through the runtime. Everything is traceable. Everything is controllable. Let me make this concrete. Say an agent needs to call a GitHub API to list pull requests. In a traditional framework, the agent receives a GitHub token and makes the HTTP call directly. The token is in the agent's memory. It appears in logs. If the agent is prompt injected, the token is compromised. In AgenticNetOS, the agent creates a data token that says, call the GitHub API endpoint pull requests repository X. That token flows to an HTTP processing step. The HTTP step, not the agent, fetches the GitHub token from the vault. The HTTP step makes the call with proper authentication, retry logic, and timeout handling. The results come back as a new data token. The agent reads the results. The agent never saw the GitHub token. The agent does not even know how the authentication works. It just knows it asked a question and got an answer. This is not a philosophical difference. This is an architectural one. And it is the reason AgenticNetOS is production-ready when other frameworks are still stuck in demos. Credentials never touch the agent. Let me be very specific about how security works, because this is the feature that makes enterprise adoption possible. In a typical agent deployment, you give the agent an API key, maybe through an environment variable, maybe through a configuration file, maybe hard-coded in a prompt. The agent uses that key to make API calls. The key appears in logs. The key sits in memory. If the agent is compromised through prompt injection, through a malicious tool, through a bug, the key is exposed. AgenticNetOS eliminates this entire attack surface. Credentials are stored in a vault, an encrypted secrets management system running on an isolated network. The vault uses AES 256 encryption at rest. Credentials are organized by model and transition. Each processing step has its own credential scope. No transition can access another transition's secrets. When an agent needs to make an API call, here is what actually happens. The agent creates a work request, a token describing what it wants to do. That token goes to an executor. The executor is a separate service that polls for work. The executor, not the agent, fetches the credentials from a vault. The executor injects the credentials into the HTTP call or shell command. The executor captures the result. The executor posts the result back as a new token. The agent reads the result. At no point did the agent see the credentials. At no point did the credentials appear in the agent's context. At no point were the credentials part of the data flowing through the system. The credentials existed only in the executor's memory for the duration of the execution and were discarded immediately after. This is credential isolation by architecture, not by policy. You do not need to trust the agent not to leak credentials. The agent literally cannot access them. The tools do not exist at the agent's permission level. The credentials flow through a completely separate channel, vault to executor to external service, that the agent has no visibility into. And it gets better. Credential rotation is seamless. Update the credential in the vault. The next time the executor fires that transition, it fetches the new credential automatically. No restart, no redeployment, no agent reconfiguration. The agent does not even know the credential changed because the agent never knew the credential in the first place. OAuth tokens with automatic refresh. API keys with versioning. SSH keys for remote execution. database connection strings, cloud provider credentials, webhook secrets, all managed in the vault, all injected by the executor, all invisible to the agent. Let me walk you through the actual security layers. The vault runs on an isolated internal Docker network. It is not exposed to the host machine. It is not accessible from the internet. Only the executor service can reach it, and only through authenticated internal calls. The vault uses OpenBow, an open-source fork of HashiCorp Vault, with KV version 2 storage that automatically versions every credential update. Every credential is stored at a path scoped to a specific model and transition. One transition cannot access another transition's credentials. Path validation blocks traversal attacks. Only alphanumeric characters, hyphens, and underscores are allowed in path segments. The Vault backend encrypts everything with AES 256 GCM at rest. In production mode, authentication uses AppRoll with automatic token renewal. In development, it uses simple token auth. And here is the operational beauty. When you need to rotate a credential because a key expired, because you detected a leak, because policy requires quarterly rotation, you update the credential in the vault through a single API call. No restart, no redeployment, no agent reconfiguration, no runtime. The next time the executor fires that transition, it fetches the new credential. The agent does not even know the rotation happened. For an enterprise security team evaluating agent deployment, this answers the first and most important question: what happens to our secrets? The answer is, your agents never see them. Your secrets live in an encrypted, isolated version vault. They travel through an authenticated internal channel to a stateless executor. They exist in memory only for the duration of a single execution. They never appear in logs, never become part of the event stream, never flow through the data model. They are architecturally invisible to every agent in the system. Every action is traceable. The second question enterprise teams ask is, what did the agent do? In most agent frameworks, the answer is, check the logs. Maybe you get a conversation transcript. Maybe you get API call logs. Maybe you get nothing because the session expired and the context window was recycled. Reconstructing what an agent did 3 days ago is often impossible. In AgenticNetOS, the answer is, everything is an immutable event. The entire system is built on event sourcing. Every token created is an event. Every token consumed is an event. Every transition fired is an event. Every agent tool call is an event. Every result produced is an event. These events are immutable. Once recorded, they cannot be modified or deleted. They form a complete, replayable history of everything that has ever happened in the system. This means you can answer questions like, what data did Agent 7 see when it made that API call on Tuesday at 3:14 p.m.? You can replay the exact sequence. You see the exact tokens the agent consumed. You see the exact tool calls it made. You see the exact results it produced. You see where those results went. But traceability in AgenticNetOS goes beyond event sourcing. Every transition emits metrics to Prometheus. Every token movement generates distributed traces via OpenTelemetry. Grafana dashboards show real-time health of every agent, every workflow, every data flow. Tempo enables full trace inspection. Follow a single piece of data from the moment it enters the system through every transformation, every agent interaction, every external call to its final destination. Open Grafana. You see all your active agents, their throughput, their success rates, their latency. One agent is running slower than usual. Click into the distributed trace in Tempo. Follow a single data token from a moment it entered the system, through the parsing step, through the classification step, through the agent investigation step, through the executor command, and back. At each step you see the duration, the input data, the output data, and any tool calls the agent made. The bottleneck is an external API responding slowly. not your agent, not your system. You know this in 30 seconds. No debugging, no log hunting, no guessing. And the audit trail goes deeper than operations. Regulatory compliance often requires you to demonstrate what data was processed, how it was handled, and what decisions were made. In AgenticNetOS, this is a query away. Every token creation, every consumption, every transition firing is a permanent, immutable event. You can generate a complete chain of custody for any piece of data in the system. Show me every operation that touched customer data in the last 30 days. The event stream answers that definitively. This is observability built into the foundation. Prometheus for metrics, Grafana for dashboards, Tempo for distributed traces, OpenTelemetry for instrumentation across every service. Not added later, not optional, not a paid add-on. Every installation of AgenticNetOS has full metrics, full tracing, full dashboard from the first agent you deploy. Because in production, observability is not a nice-to-have. It is the difference between controlled operation and blind hope. Stop everything with one click. The third question enterprise teams ask is, how do I shut it down? In most agent frameworks, stopping an agent means killing a process. Maybe you find the right PID. Maybe you terminate the container. But if the agent spawns subprocesses called external services or trigger downstream workflows, those continue running. There is no centralized control. There is no single point where you can say stop everything. In AgenticNetOS, every agent runs as a transition inside the runtime. Transitions have explicit lifecycle states: deployed, running, stopped. You can stop a single transition. You can stop all transitions in a workflow. You can stop every transition in the entire system. One action, immediate effect. When you stop a transition, it stops polling for work. No new tokens are consumed. No new actions are taken. Work in progress completes. You do not lose partial results, but no new work begins. The agent is frozen in a known state. You can inspect that state. You can see what tokens are waiting. You can see what results were produced. Then you decide, resume, modify, or tear down. From the CLI, stop all transitions in the log analyzer net. Done. From Telegram, pause the code review pipeline. Done. From the GUI, click the stop button on the net. Done. And because the system is event-sourced, stopping is not destructive. Every piece of state is preserved. Every token remains in its place. When you resume, the system picks up exactly where it left off. No data loss, no state corruption, no reinitialization needed. There's also a deeper level of control. Agent transitions in AgenticNetOS operate with a permission system modeled after Unix file permissions. 4 permission flags: read, write, execute, and HTTP. A read-only agent can query data and inspect the system structure, but cannot change anything. Perfect for monitoring and reporting. A read-write agent can also create data, build new containers and processing steps, and set up logic, but cannot activate or deploy what it builds. A read-write-execute agent can deploy and fire transitions, run commands. A full-access agent can also make external HTTP calls. This means you control not just whether an agent runs, but what it can do while it runs. A reporting agent gets read-only access. A designer agent gets read-write. It can build elaborate workflows, but physically cannot deploy them. A human reviews the design, approves it, and deploys. The agent proposes. A human decides. This boundary is architectural. The deployment tools simply do not exist at the read-write permission level. Start conservative. Give new agents read-only access. Watch their behavior. Promote to read-write when you trust them. Promote to execution when the workflow is proven. You never give full autonomy on day one. Trust is earned through observable behavior in a transparent runtime. This is operational control. Real operational control. Not kill the process and hope the cleanup handlers work. Structured, state-preserving, permission-bounded, resumable stop and start. You know what every agent costs. The fourth question, how much is this costing me? AI agents consume resources. LLM API calls cost money. Compute time costs money. External API calls may cost money. And when agents run autonomously, costs can escalate quickly. An agent that retries a failing operation 50 times. An agent that requests a large language model response for a task that could be handled deterministically. An agent that makes redundant external calls because it forgot it already has the data. AgenticNetOS gives you full cost visibility because every action is a measurable event. Every LLM call goes through a track transition. You know how many calls each agent makes, how many tokens each call consumes, how long each call takes. Every external API call goes through an HTTP transition with metrics. Every command execution goes through an executor with duration tracking. Prometheus collects it all. Grafana visualizes it. You can see cost per agent, cost per workflow, cost per day. You can set alerts. If an agent exceeds its expected call count, you get notified. If a workflow's cost spikes, you see it immediately. But AgenticNetOS does something more interesting than just tracking costs. It reduces them over time. Here is how. When an agent solves a problem, the solution can crystallize into a deterministic processing step. The first time the log analyzer encounters a database timeout, an AI agent reasons through the error, 5 LLM iterations, about 5 cents. The analysis produces a reusable pattern. The next time the same error occurs, a simple routing rule matches the pattern instantly. 0 LLM cost. The first encounter costs 5 cents. The second costs 1/100th of a cent, 500 times cheaper. By month 2, 80% of common errors match known patterns. The AI handles only the genuinely novel cases. Let me put real numbers on this. Imagine a monitoring system processing 500 log events per day. Month 1, every event requires AI analysis. 5 cents per event, $25 per day, $750 per month. By month 2, 60% of events match crystallized patterns. Only 200 events need AI. $10 per day, $300 per month. By month 6, 90% crystallized. 50 events per day need AI. $2.50 per day, $75 per month. Same volume, 90% cost reduction. Compare that to a traditional AI integration where every event triggers an LLM call forever. $750 per month, every month with no learning. AgenticNetOS turns that into $750 the first month and $75 by month 6. The savings compound year over year. Your AI bill goes down over time, not up. Most AI deployments see costs scale linearly with usage. More agents, more calls, more cost. AgenticNetOS inverts this. More usage means more patterns learned, more deterministic routes, less AI needed. The system gets cheaper as it gets smarter. Agents that build agents. Now let me tell you what this system actually does in practice. Because the theoretical architecture is important, but what matters is what it enables. The primary use case of AgenticNetOS is this. You describe a problem in natural language, and the system creates a team of specialized agents that solve it. Not one agent. A team. Multiple agents, each with a specific role, working together in a coordinated workflow with explicit data handoffs, permission boundaries, and traceable interactions. Here is a real example. You tell the system, build a code review pipeline that reviews security across my gateway, vault, and CLI modules. The system creates an orchestrator agent that understands the request. The orchestrator creates 3 specialist agents, one for each module. Each specialist reviews the code, identifies issues, proposes fixes. The fixes flow to a testing stage where command transitions build the code and run test suites. Results flow back to a verification agent that decides, pass, retry, or escalate. This is not hypothetical. This pipeline ran on AgenticNetOS and produced real results. The gateway review took 103 seconds, found issues, fixed them in 63 seconds, tests passed in 10 seconds. The Vault review discovered a high-severity path injection vulnerability, a real security bug, and fixed it in 6 minutes with new tests. The CLI review found and fixed code quality issues in under 6 minutes. 3 modules. Parallel processing. Security vulnerability discovered and patched. All from a single prompt. All fully traceable. All with credentials isolated from every agent. The GitHub token used to access the repositories. In the Vault. The CI server credentials used to trigger builds. In the Vault. The agents never saw any of them. Another example. The QA validation system. 8 independent quality checks, build verification, type checking, dependency audit, bundle size analysis, shebang validation, structure verification, module export checks, and cross-package resolution. Each check runs in parallel via command transitions on executors. Results flow to a collection point. An agent analyzes the aggregate results and produces a quality report. No YAML. No Jenkins pipeline. No GitHub Actions configuration. A prompt created the entire quality assurance system. And because it runs inside the AgenticNetOS runtime, every check is traceable, every failure is diagnosable, and the entire pipeline can be stopped, modified, and restarted through conversation. And here is something that happened during the development of the QA validation system that illustrates why a runtime matters. 6 bugs were discovered during live execution. Token wrapping issues, expression resolution errors, catch-all routing semantics, payload handling, process management, and exit code interpretation. In a traditional framework, these bugs would have been invisible, silent failures in a chain of API calls. In AgenticNetOS, every one of them was visible because every token, every transition firing, every piece of state is observable. The bugs were found, diagnosed, and fixed within the system itself. The system's transparency made debugging not just possible, but natural. The executor pattern, how agents reach the outside world. Let me explain the executor pattern in detail, because it is the architectural decision that makes all of this secure. In AgenticNetOS, there are 2 kinds of processing. Things that happen inside the runtime, and things that happen outside. Inside the runtime, agents read data, reason about it, create new data, route decisions. This is the thinking layer. It runs on a master service, is fast, observable, and fully controlled. Outside the runtime, commands execute on remote machines, API calls reach external services, files are read and written on distributed infrastructure. This is the doing layer. It runs on executor services. The executor is a separate process that runs wherever you need execution to happen. On a cloud server, on a developer laptop, inside a corporate network behind a firewall, on an edge device. The executor does not accept inbound connections. It polls the master every 2 seconds, asking, "Do you have work for me?" This egress-only pattern means the executor works anywhere with outbound internet access. No open ports, no VPN, no firewall rules, no service mesh configuration. The executor reaches out. Nothing reaches in. When a master has a command to execute, the executor picks it up. The executor fetches credentials from the vault. Not the master, not the agent, the executor. The executor runs the command locally. It captures the output, standard error, exit code, duration. It posts the results back to the master as new data tokens. The agent sees the results. The agent never sees the execution. The agent never sees the credentials. The agent never touches the external system directly. This is the virtual runtime concept. The agent thinks it is making things happen. In reality, the agent is creating requests that flow through a governed execution channel. The channel handles authentication, timeout, retry, result capture, and audit logging. The agent stays inside the sandbox. The executor does the outside work. And because executors are stateless and independent, you can scale them freely. Need more execution capacity? Start another executor. It polls the master. It picks up work. No coordination needed. Need execution in a different network? Deploy an executor there. It polls through the gateway. Same system, different location. 10 executors processing work in parallel across 3 data centers, all controlled by a single master, all credentials managed in one vault, all fully traceable through one monitoring stack. That is the deployment model AgenticNetOS enables. And the executor model has a practical advantage that matters for teams adopting AI agents gradually. You can start with one executor on a developer laptop, run some experiments, prove the value, then deploy an executor on a staging server, then production. Each executor just polls the same master. No infrastructure changes, no migration, no big bang deployment. You scale adoption as fast or as slow as your organization is comfortable with. The executor also handles long-running operations gracefully. A Claude code session that takes an hour to review and fix a complex code base. The executor runs in the background. The polling thread continues handling other transitions in parallel. Configurable timeouts, up to 4 hours per command, prevent runaway operations without killing legitimate long-running work. And if a command does time out, the result is a structured error token that routes to an escalation path. Nothing is lost. Nothing is silent. What is running today on alexcjsaylor.com? Let me tell you what is actually running today, documented with full case studies at alexcjsaylor.com. These are not roadmap items. These are production systems. The autonomous code review and fix pipeline. 3 interconnected agent networks that review code across 8 service modules in parallel. Each module gets a dedicated review agent. The agent reads the code, identifies issues, security vulnerabilities, code quality problems, missing error handling. A fix agent proposes patches. A command transition builds the patch code. A test transition runs the test suite. A verification agent evaluates the results. Real result: a high-severity path injection vulnerability discovered and fixed in the Vault service. The agent identified that path parameters were not being validated, allowing directory traversal attacks. It wrote the fix and the tests. Total time, 6 minutes. A human security auditor would have found this too. Eventually, the agent found it, fixed it, tested it, and reported it in the time it takes to make coffee. The self-improving log analyzer. 19 data containers, 12 processing steps, 6 functional zones. This is the system that demonstrates the cost crystallization pattern most dramatically. Feed it 213,000 log lines from a distributed microservices system. The first time it encounters a database connection timeout, an AI agent investigates. It traces the error across 3 service logs. It correlates timestamps. It identifies that the connection pool on the order service exceeded its maximum at the same time a batch job held connections for unusually long durations. Root cause: connection pool exhaustion triggered by concurrent batch processing during peak load. 5 to 7 LLM iterations. About 5 cents. But the analysis produces more than just a diagnosis. It produces a reusable error signature, a structured pattern that says, when you see this error code with these connection pool metrics with this concurrent query count, the root cause is known. That signature becomes a token in a learning container, a deterministic matching rule. Next time the same error pattern occurs, instant recognition. A simple routing step matches the signature. 0 AI cost. 0 LLM iterations. The diagnosis is attached immediately. 500 times cheaper than the first encounter. By day 4, the most common patterns are crystallized. By month 2, 80% of errors are handled deterministically. The AI handles only genuinely novel errors, the ones the system has never seen before. The cost curve bends downward with every investigation. The system learns by doing its job. The 25 cycles training loop, a self-improving system that pushes the boundaries of autonomous operation. 15 data containers, 12 processing steps, a closed feedback loop where the system reads its own execution logs, identifies failures, proposes code fixes via Claude code command execution, applies the patches, rebuilds the affected services, tests the results, generates a report, and feeds a new task back to the beginning. 25 complete cycles. 6 hours. 0 human intervention. After cycle 1, the agent had 1 context token, its own execution report. By cycle 5, it had 5 context tokens and had already identified a recurring serialization error pattern. By cycle 10, it was proactively checking for that pattern before submitting code. By cycle 15, it was avoiding mistakes from cycle 3 without being explicitly told to. It read its own history, recognized the failure pattern, and adjusted. The cost per cycle decreased as context accumulated. Each execution report became knowledge for the next cycle. The system got more efficient over time, not less. The opposite of what you see in most AI systems where longer conversations degrade performance. All of this running inside the governed runtime. Every cycle traceable. Every code change auditable. Every cost measurable. And stoppable at any moment. The developer net. 12 processing steps across 6 functional zones. Takes a feature specification in plain English and produces staged, tested, reviewed code. Here is a real execution. Input. Add a health check endpoint that returns service status and uptime. The planning step, an LLM transition, analyzes the specification, identifies affected files, and proposes an implementation approach. The implementation step, a command transition, invokes Claude code with a detailed prompt derived from the plan. Claude code generates the actual source files. The testing step, another command transition, runs the full test suite and captures results including exit codes, test counts, pass counts, and failure details. The review step, an agent transition using a different AI model for independence, reviews the code changes against the original specification and decides, approve, request revisions, or escalate to a human. The net includes retry loops. If tests fail, a routing step evaluates the failure and reroutes the task back to implementation with the failure context attached. The second attempt has strictly more information than the first. It knows what failed and why. Up to 3 automatic retries before human escalation. Time budgets prevent runaway execution. 10 minutes for analysis, 2 hours for implementation, 10 minutes for testing. Complete REST endpoint. Planning through review in under 4 minutes. A reproducible development methodology encoded as structure, not documentation. The methodology is not in a wiki nobody reads. It is in the topology of the workflow. It executes the same way every time. And when you want to change the methodology, add a security review step, change the testing threshold, switch the review model. You modify the workflow through a prompt. The change takes effect immediately. The Intel Gather platform. This is the most complex system running on AgenticNetOS. 9 interconnected nets. 55 processing steps. 35 shared data containers enabling cross-net communication without a single line of integration code. The system crawls websites, monitors forums, pulls RSS feeds, watches channels, analyzes everything it finds with AI classification, synthesizes knowledge across sources, and publishes structured intelligence reports. Each processing stage is a separate subnet. The scanner discovers entities and writes data to a shared analysis container. The analyzer reads from that same container identifier, same runtime data pool, classifies each entity, and writes structured findings to a shared reporting container. A knowledge graph subnet maintains relationships between entities. A synthesis subnet reads accumulated findings and produces reports. Adding a new data source means adding one container and one processing step, not writing a new microservice, not building an integration pipeline, not configuring a message queue. One container, one processing step connected with an arc. The new source starts flowing through the existing analysis and reporting infrastructure immediately. This is the power of composable architecture. New capabilities plug in without disturbing existing flows. The reflexive brain, a system that asks questions about its own code base, generates answers, identifies knowledge gaps, investigates deeper, and synthesizes what it learns into structured knowledge tokens. 15 data containers, 18 processing steps. After 3 cycles, 31 knowledge tokens covering API patterns, architectural decisions, and cross-service dependencies. 12 architecture insights that would have taken a human developer days to compile. The knowledge accumulates in context containers with non-consuming reads. Every cycle, the agent reads all existing knowledge before answering a new question. The answers get richer. The context gets deeper. Documentation that writes itself, updates itself, and improves itself through the natural process of using the system. The QA validation system. 8 independent quality checks running in parallel. Build, type check, dependencies, bundle size, structure, modules, cross-package resolution. All automated, all traceable, all running inside the governed runtime. Results aggregate automatically. Failures route to investigation agents. The Bootstrap agent. One more system that deserves mention because it demonstrates self-management. Every workspace needs initial data, context documents, tool configurations, learning seeds. Previously, a fragile shell script made 9 sequential API calls. If one failed, you started over. I replaced it with a single agent transition. The agent reads a definition describing what data should exist, then creates it. 9 tokens created, 11 iterations, 6 minutes and 48 seconds, 0 failures. And while the agent was still creating data, downstream processing steps had already started working on the first items. The system did not wait. It started processing the moment the first piece of data appeared. If a system can set up its own state, it can also repair its own state. Self-initialization is the first step toward self-healing. These systems are not demos. They produce real results. They run inside the AgenticNetOS runtime. They are fully observable through Grafana dashboards. Their costs are tracked per transition through Prometheus metrics. Their credentials are isolated in the vault, and they can all be stopped with a single command. Why this is the first production-ready framework. Let me be direct about why I call AgenticNetOS the first production-ready multi-agent orchestration runtime. This is not marketing language. It is a specific technical claim based on 5 requirements that production deployments need and that no other framework provides in combination. Requirement 1, credential isolation. Agents must never see production credentials. In AgenticNetOS, credentials flow through a completely separate channel, vault to executor, that agents have no access to. LangChain, Crew AI, AutoGen. In all of these, agents receive credentials directly or through environment variables that the agent can read. Requirement 2, full audit trail. Every action must be traceable and replayable. AgenticNetOS is built on event sourcing. Immutable events recording every token creation, consumption, transition firing, and tool call. Most agent frameworks provide logs. Logs are not audit trails. Logs can be incomplete, inconsistent, or missing. Events are immutable and complete. Requirement 3, operational control. You must be able to stop, resume, and modify agents without losing state. AgenticNetOS provides lifecycle management for every transition. Deploy, start, stop, resume. State is preserved in tokens that persist independently of agent lifecycle. In most frameworks, stopping an agent means killing a process and losing all intermediate state. Requirement 4. Cost visibility and control. You must know what each agent costs and be able to limit it. AgenticNetOS tracks every LLM call, every external API call, every command execution through Prometheus metrics. And the crystallization pattern actively reduces costs over time by converting AI reasoning into deterministic logic. Requirement 5. Multi-agent coordination. Agents must work together with explicit data handoffs, not through shared conversation contexts. AgenticNetOS provides shared data containers where multiple agents can read and write tokens with atomic consumption guarantees. No race conditions. No duplicate processing. No lost data. Compare this to frameworks where multi-agent coordination means agents talking to each other in a chat thread. No atomicity, no ordering guarantees, no structured handoffs. No other framework provides all 5. Some provide 1 or 2. AgenticNetOS provides all 5 because they are architectural properties, not add-on features. Let me be specific about the competition. LangChain gives you chains and agents with tool calling. It is excellent for prototyping, but credentials pass through the agent. State is ephemeral. There is no built-in audit trail. There is no visual editor. There is no executor sandbox. There is no cost tracking beyond what you build yourself. LangChain solves the how to call an LLM problem. AgenticNetOS solves the how to run agents in production problem. Crew AI give you multi-agent teams with role definitions. Agents talk to each other in structured conversations. But the coordination is conversational, not transactional. 2 agents can process the same item. There is no atomic data consumption. Credentials flow through agent configurations. The state is in memory. Stop the process, lose the state. AutoGen gives you multi-agent conversations with sophisticated interaction patterns. But it is fundamentally a conversation framework. Agents share a chat thread. The state is the conversation history. When the conversation ends, the state is gone. There is no runtime, no sandbox, no credencial a uselación. Temporal gives you durable, fault-tolerant workflow execution. It is genuinely production-grade for deterministic workflows. But adding AI intelligence requires custom activities, escape hatches that break the workflow model. There is no concept of an agent transition that reasons through multi-step problems autonomously within the workflow structure. And there is no credential isolation at the transition level. You cannot bolt credential isolation onto a framework that was designed to pass API keys to agents. You cannot add event sourcing to a framework built on ephemeral conversation state. You cannot add a visual editor to a framework that has no structured topology to visualize. These properties must be fundamental to the architecture. In AgenticNetOS, they are. The architecture you do not need to think about. I want to address something briefly. AgenticNetOS is built on a mathematical formalism called Petri nets, a model for concurrent, stateful systems invented in 1962. But you do not need to know this to use the system. You do not need to understand the theory. You do not need to learn a new modeling language. What you need to know is what the architecture gives you. It gives you explicit state. Every piece of data is in a known location at all times. You can see it. You can query it with a purpose-built query language called RQL. You can trace how it got there. There is no hidden state. There is no, the agent is thinking about something, but I cannot see what. Every token of data, in every container, at every moment, is visible and queryable. It gives you safe concurrency. Multiple agents can work in parallel without stepping on each other. Atomic data consumption, using compare and swap operations, means 2 agents never accidentally process the same item. This is not a best practice you hope developers follow. This is guaranteed by the mathematics of the underlying formalism. 60 years of proven theory. No race conditions. No duplicate processing. No lost data. It gives you natural workflow composition. Simple building blocks compose into complex workflows. A monitoring agent feeds into an analysis agent feeds into a notification agent. Each one is independent. Each one is replaceable. The data flows between them through explicit channels. Want to add a security check between analysis and notification? Add one container and one processing step. The existing agents do not change. The new step plugs into the flow naturally. It gives you a data query language. RQL lets any processing step specify exactly which data to consume. Select tokens where the status equals active, order by timestamp, limited to 5 results. Filter by any field in the data structure. Combine conditions with and or. The query language is how you express which data should this agent work on, precisely, declaratively, without writing code. It gives you 7 types of processing steps, and this is worth understanding because it is what makes the system so versatile. The first type is routing. You have a piece of data. Based on its content, is the status urgent or routine? Is the amount above a threshold? Is the category known or unknown? The data moves to different destinations. No AI involved. No cost. Just conditional routing. This is the railroad switch of the system. The second type is transformation. Data comes in one shape and goes out another. Field renaming, structural mapping, metadata injection, format conversion. A template engine handles it. No AI, no cost, just mechanical reshaping. The third type is external API calls. Call a REST endpoint with full enterprise reliability. Retry with exponential backoff, multiple authentication methods, timeout handling, idempotency protection. Credentials fetched from a vault by the executor, never visible to agents. Error responses route to different paths than success responses. The fourth type is AI reasoning. Single-shot inference. One question, one answer. Classify this ticket. Summarize this document. Extract these entities. The model responds. The response becomes data. Fast, bounded, predictable cost. The fifth type is autonomous agents. Multi-step problem solving with access to over 40 tools. The agent can read data, navigate relationships, create new data, reason through complex problems, and produce structured output. This is the most powerful type and the most expensive, which is why the system is designed to use it only when the other types cannot handle the task. The sixth type is command execution. Shell commands running on remote executors behind the credential isolation pattern. Build a project, run tests, execute a script, invoke a CLI tool. All sandboxed, all traceable, all timeout protected. The seventh type is structural relationships. Semantic connections between data containers that agents can navigate to discover related context. An agent investigating an incident follows links from the runbook container to the past incidents container to the lessons learned container. The agent builds understanding through the system's own topology. 3 of these types cost nothing. No AI, no external calls, just data movement. 1 builds structure without ever executing. The AI steps handle only what genuinely requires intelligence. The system is designed to minimize cost by default. Every workflow starts with intelligence handling everything. Over time, as patterns emerge, the intelligent steps crystallize into deterministic ones. The cost curve bends downward. You interact with all of this through prompts. You say create a monitoring pipeline. The system selects the right building blocks, constructs the topology, wires the data flows, sets up the logic. You never manually define any of this unless you want to. The GUI shows you the result. You can adjust through further prompts. Who should use AgenticNetOS? Let me be specific about who this is for and what problems it solves. If you're building a single-agent chatbot that answers customer questions, you do not need AgenticNetOS. Use LangChain. Use the Anthropic API directly. A single agent with a system prompt is fine for that use case. If you are building multi-agent systems that need to run in production, systems that handle enterprise data, use production credentials, require audit trails, need cost control, and must be operationally manageable, then AgenticNetOS is built for exactly that. The sweet spot is enterprise automation where you need governed intelligence. Monitoring systems that watch logs, identify patterns, and escalate issues, with full traceability of what was detected and what actions were taken. Audit and compliance workflows where every decision must be recorded and replayable. DevOps pipelines where code is reviewed, fixed, tested, and deployed by agents, with credential isolation, cost tracking, and the ability to stop everything at any moment. Data processing pipelines where multiple agents work on different aspects of the same data, with atomic handoffs and no duplicate processing. Intelligence gathering and synthesis across multiple sources, with structured knowledge accumulation and full provenance tracking. The common thread. These are all scenarios where the agent is doing real work with real consequences, and you need to trust but verify. AgenticNetOS provides the verify part that no other framework offers. And here's who this is not for. If you're experimenting with AI agents on your laptop with no production data, use whatever framework is most convenient. If you're building a simple chatbot, you do not need an orchestration runtime. If you have one agent doing one thing, the overhead of a full runtime is not justified. AgenticNetOS is built for the moment when your agent project crosses the line from experiment to production, when real data is involved, when real credentials are at stake, when real money is being spent, and when real consequences follow from agent decisions. That is the line where every other framework stops. That is where AgenticNetOS begins. Getting started in 5 minutes. Here is how you go from zero to running agents. Start the system. Docker Compose brings up the core services, the data engine, the orchestration engine, the visual editor, the gateway, the executor, and the vault. One command. Services come up. Ports are assigned. Open the CLI. Type Agentic-Chat. You're now in a conversation with the system. The system has tools to create data containers, processing steps, connections between them, and the logic that drives each step. It has access to the full API. Everything you can do in the visual editor, you can do through this conversation. Describe what you want. Create a monitoring agent that watches for error patterns in application logs and creates summary reports every hour. The system thinks. It creates the containers, incoming logs, error patterns, known signatures, reports. It creates the processing steps, log parsing, pattern matching, AI classification for unknown patterns, report generation. It wires them together. It sets up the logic. Deploy and start. Deploy all transitions and start them. The system activates every processing step. They begin polling for data. Drop a log file into the incoming logs container, either through the API, through the CLI, or through another automation. Watch the data flow through the pipeline in the visual editor. See errors get classified. See patterns get matched. See reports get generated. From this point, everything is manageable through conversation. Show me what errors were found today. Stop the report generator. Add a Slack notification when critical errors are detected. What's the cost of running this pipeline for the last week? 5 minutes from Docker Compose to running agents. Everything created by prompting. Everything visible in the GUI. Everything traceable through metrics and events. Everything stoppable through a single command. Now let me tell you what happens as you grow. Your first workflow works. You build a second one. A third. You have 5 agent workflows running, each with multiple processing steps, each with its own data containers and executor assignments. The visual editor shows you all of them. You can drill into any one. You can see the data flowing through each in real time. You can trace any piece of data across any workflow. You package your best workflow. Publish it to the package registry. A colleague on another team installs it. They point it at their vault with their credentials. They customize the prompts for their domain. They are running in minutes, not weeks. The same governed, traceable, credential-isolated runtime. Different data, different credentials, same guarantees. The visual editor is your observation deck. The CLI and Telegram are your control surfaces. The runtime handles security, traceability, credential isolation, cost tracking, and operational control. You focus on describing what your agents should do. Agentic-NetsOS handles everything else. What comes next? The package registry is live. Package a working agent workflow, publish it, share it with others. 3 scopes: topology only, topology with logic, or a complete ready-to-run package, including seed data. Install someone else's monitoring pipeline. Customize the error patterns for your infrastructure. Run it inside your runtime with your credentials in your vault. The reflexive capability is operational. Systems that monitor their own performance, identify when an agent is degrading, propose optimizations, and deploy them under human approval. Self-improving automation governed by the same runtime that makes it auditable and safe. Multi-master federation is on a roadmap. Multiple orchestration engines behind a single gateway. Model-based routing. Different teams own different agent workspaces, all managed through one control plane. The gateway already supports master registration and heartbeat. It already performs model-based request routing and fan-out aggregation across multiple masters. Scale from a single developer to an organization without changing the architecture. The CLI already supports multiple LLM providers: Claude, OpenAI, Ollama for local models, Codex, Gemini. You can use a fast, cheap model for routine tasks and a powerful reasoning model for complex problems. The system routes intelligently between worker models and thinker models based on task complexity. Local models mean your prompts and agent reasoning stay on your infrastructure. No data leaves your network. But here's the point I want to leave you with. The era of deploying naked agents is ending. Not because the technology will fail, it works brilliantly, but because organizations will demand the same governance for AI agents that they demand for every other system that touches production data. Credential isolation, audit trails, cost control, operational management, traceability. These are not optional features for enterprise deployment. They are table stakes, and they must be architectural properties, not afterthoughts. Agentic-NetsOS is the first runtime that provides all of them. Every agent governed, every action traceable, every credential isolated, every cost measured, everything created by prompting, everything stoppable with one click. The agents do not run naked anymore. They run inside a runtime that was built for exactly this purpose. And everything you just heard, every capability, every security property, every real system running today was built by one developer in 9 months with AI coding agents as the only collaborators. Over 182,000 lines of code across 10 services. The system that governs agents was itself built with the help of agents, which might be the most fitting origin story an agent orchestration runtime could have. The system is available today. Business Source License 1.1 for the source available components. Free for non-commercial use, converting to Apache 2.0 in 2030. The core runtime is available as pre-built Docker images. The surrounding services, the gateway, the executor, the vault, the CLI, the chatbot, the blob store, are fully open source on GitHub. Over 40 detailed articles at alexcjsaylor.com cover every aspect of the system, from getting started to advanced multi-agent orchestration patterns. Docker Compose Up. 5 minutes. Your first agent running inside a governed, traceable, credential-isolated, cost-tracked, visually observable, instantly stoppable runtime. That is what production-ready means. Your agents are waiting for a home. Agentic-NetsOS is that home.